so we got a velocity versus time graph. In this velocity versus time graph, we have an object that is doing a whole bunch of different things. Okay? In the first 2 seconds of this graph, what is the object doing? In the first 2 seconds? Not moving. Yeah, it has a velocity of 0, right? The line is going right along the x-axis for the first 2 seconds. So the object is sitting still for the first 2 seconds. Then we see that its velocity changes from 0 to -3. What is it doing? Not just backing up, it's
Going back.
not just going backwards. How is it going backwards? Is it going at a constant velocity or accelerating?
Accelerate.
It's accelerating. Okay? It's accelerating backwards because the graph shows us that its velocity changed from 0 to -3. Okay? That's an acceleration. Anytime the velocity changes, the object is accelerating, even if it's backwards. Okay? Everybody okay with that? Because probably a lot of us were looking at that graph and going, oh, diagonal lines mean a constant velocity. They do on a, what kind of graph? On a position time graph. Again, that's why we don't want to memorize. Okay? If we memorize, that's the kind of mistake we'll make. Okay? We want to analyze each graph as we come to it. I look at this graph and say, all right, velocity, it went from 0 to -3 meters per second. That's an acceleration, not a constant velocity. Okay, what's it doing between 5 seconds and 7 seconds? It's accelerating which direction? Forwards. Okay? It's accelerating forwards during that part. Is it moving forwards the entire time? Okay? At time 5 seconds, its velocity is -3 meters per second. Which way is it going at 5 seconds? Forwards or backwards? If its velocity is -3, it's going backwards. Okay? By the end of that section, if velocity is +2, which means at the end of that, it's going forwards. Okay? So during that section, it accelerated positively, but that actually means it changed direction during that part of the graph. Okay? It would be like if I put a bungee cord across the front of the classroom and ran into the bungee cord. Okay? I'd still be moving forwards at the beginning, okay? But eventually the bungee cord would stop me and throw me back the other direction. Okay? Does that make sense to everybody? I can, the whole time I'm in contact with the bungee cord, my acceleration would be this way. But I'd only be moving this way at the end. Okay? That's to slow me down and stop me first and then throw me back the other way. Okay? The whole time though, I'm accelerating. It's like when you throw something up in the air. Okay? If I throw this thing up in the air, as soon as it leaves my hand, its acceleration is which way? Down. Because once it leaves my hand, the only force acting on it is gravity. Okay? And so gravity accelerates it downwards, which means it first has to slow it down and stop it, and then it can actually fall. Okay? But the whole time it's accelerating downwards. It just doesn't move downwards the entire time. Okay? So it's possible to accelerate one way while moving a different way. Okay? Eventually, the two are going to match up. Okay? All right, what's going on between 7 and 12 and 12 seconds, I guess. 7 and 12 seconds. How fast is it going at 7 seconds? +2. How fast is it going at 12 seconds? +2. What's it doing during that section? Yeah, it's traveling at a constant velocity of +2 meters per second. Okay, and again, I'm not memorizing that, I'm just looking at the graph and going, it's showing me how fast it's going, and it says that for those seconds, it is going 2 meters per second forward. Okay. All right, what's going on in this section of the graph? We start out at +2 and we end at -6. What's the object here? Is its velocity changing during that time? What do we call that? Starts with A. It's accelerating. Yeah. Okay. It's accelerating during that time. Okay? It's accelerating negatively because it starts out in a positive direction and ends up going negatively quite quickly, actually. All right, and then during the next section there, okay, we see another acceleration, but this time it's positive or negative? Positive, yeah. Okay, and then there's a little part here where we're going at a constant velocity of -2 meters per second, and then there's another acceleration here, and then we're stopped for the last second. All right, that's the kind of interpretation I would ask you to do, okay, on a graph on a test. All right, so we just did a question on the quiz where we had to calculate the displacement of the object, okay, and we said that doing that means taking the average velocity and multiplying by time, which on a velocity versus time graph, the little trick is that that's essentially the area between the line and the x-axis. So lots of shapes to draw for this question. So I'm going to give you a couple minutes, and I want you to draw all the shapes that you're going to have to calculate the area of. Okay, so it's going to take you a little bit of time probably. This is in your digital workbook. Right, if you want to have like a digital copy of it, just open up the digital workbook, it is in there. Okay, so it's in your physics workbook package, and it is on page 4. Bottom of page 4 is where you'll find that one. Okay, I'll give you guys a few minutes there. The answers are there in bold. Right, so if you want to check and see if you did it right, but that first little bit, finding the total displacement is part B because we did the acceleration yesterday, right? So that's probably going to take you a little while, but I'll give you a few minutes to get the shapes drawn, and then I'll draw the shapes as well, and you can match it up and see if you got all the right ones. Okay, so let's look at the shapes we got to calculate. Obviously, for the first 2 seconds, there's no shape. It's on the x-axis. I can't draw anything between the line and the x-axis if the line is the x-axis. Okay. But I have after that 2 different triangles that I would need to calculate the area of. One in which the acceleration is negative and another one in which the acceleration is positive. Okay, so I would have these 2 triangles here. Right? Then I would have another small triangle right there, a big rectangle and another small triangle. Right? I would have a big triangle right here, a triangle right there with a rectangle underneath it, and a triangle there. Those would be the shapes I would have to get the area of. Yep. Okay, now, you have to read the graph carefully. Some of them have a base that is less than a second, right? There's one there that has a base of ½ a second and one that has a base of 1½ seconds. Okay, so you've got decimals in there to keep in mind when you're calculating those areas, all right? So I'll give you a few minutes to get the calculations done on those, and then I'll walk you through it, okay? And we'll look at the rest of the questions in there. Okay, so we got to find the areas of all these shapes, okay? So our first shape here is a triangle. The base of that triangle is 3 seconds. The height of that triangle is -3 meters per second. So -3 times 3 is -9. Okay, but it's a triangle, so divide it by 2, and you've got that this one here is -4.5 meters. Okay, our next triangle here has a base of 1 and a height of -3. Okay, so -3 times 1 is -3, divided by 2 because it's a triangle. Okay, we're looking at -1.5 meters. Okay, then we have this triangle here, base is 1, height is 2, 2 times 1 is 2, divided by 2 is 1 meter. Then we have this rectangle that is 1, 2, 3, 4, 5 on the base and 2 high. It's a rectangle, so just base times height, that's going to be 10 meters. Okay, then we have this really tiny triangle that's 1/2 on the base, 1/2 a second, and 2 high. So 2 times 1/2 is 1, divided by 2 is 0.5. Okay, and then we've got this triangle here that is 1.5 on the base and -6 high. -6 times 1.5 is -9. Okay, divided by 2, because it's a triangle, is -4.5 meters. Okay, I've got this triangle here that goes from -2 to -6, so it's -4 high, and it is 2 on the base, so -4 times 2 is -8, divided by 2 is -4 meters. And then I've got this rectangle that's 1, 2, 3, 4 on the base and -2 high, so that'll be -8. And then I have this last little triangle that's 1 on the base and -2 high. Okay, so 1 times -2 is -2, divided by 2 is -1. Right, so that's all the numbers that we've got to put together. Right, so -4.5, and I have to keep the negatives because this is, I'm looking for a vector quantity here. Okay, so I'll have -4.5 plus -1.5 is -6. Okay, plus +1 is -5. Plus 10 is +5, and plus 0.5 is +5.5, and then plus -4.5 will take me back to +1, and then this will take me to -3, -11, and another negative is -12. Is that what I got? Okay, 12 here too. Okay? Everybody all right with that? I would never give you one that long on a test, okay? Because you're basically doing the same thing like 10 times there, right? I would give you more like what you got on the quiz today, 3 shapes, okay, if you're gonna have to do it. Right? Questions on how we did that one? It's a bit repetitive, but once you get the pattern, they all work pretty much the same way. Okay, now what we wanna try and work towards here is to find, kind of patterns or shortcuts in some of the questions. And if we look at graphs carefully, we can sometimes save ourselves some work. There's no way to save ourselves work in that graph. Okay, everything is kind of random and we just have to do every single piece. This graph, however, may have a way to shortcut. Okay, it is a velocity versus time graph. Okay, and the first thing they want you to calculate is the total displacement over the whole trip. Okay. So the first section is 5 seconds, the second section is 5 seconds, third section is 5 seconds, last section is 5 seconds. Okay, so each part of that graph is 5 seconds in length. So you're looking for the total displacement. Okay. Oh, sorry, we forgot to finish off that other question. Sorry, let's go back to that. So part C was calculate the average velocity over the whole trip. Did I just do the hard part of finding average velocity? Okay, because average velocity is total displacement, which I just calculated, divided by total time. So I can just plug in that number I got, -12 meters, and divide it by 20 seconds. Okay, and that's going to give me -0.6 meters per second. Okay, and then the last part wants the acceleration between 14 and 20 seconds. Remember that this is our acceleration formula. A equals VF minus VI over T. So if I'm looking between 14 and 20 seconds, okay, so at time 20 seconds, my velocity is what? 0. Okay. And at time 14 seconds, it is -6. And between 14 and 20 seconds are how many seconds? 6 seconds. Okay, so 0 minus -6, okay, is going to be +6 over 6 seconds. That looks like it would be an acceleration there of, for part D, +1 meter per second squared. Okay, and then the last part wants average speed. Now, again, you've done a lot of the work for that already. But what do you need to change about the work you did?
Take out all the negatives.
Right. Take out all the negatives. Average speed is total distance over total time. All these numbers you calculated are right. Take the negatives off all the negatives, because distance only ever gets bigger. Okay, so you put all of those together, okay, so this will be 4.5 and 1.5 is 6, 7, 17, 17 and a half, 21, 25, 33, 34, 34 over 20 should give you 1.75, okay, or 35 over 20 if I counted wrong. Okay. Everyone okay with that? Okay. All right, back to this graph here. Give you a few minutes on that one. It's the next one on the sheet if you're looking at it on your phone, it's number 5. Okay, so just in case you've lost your formula sheet, that's the formula for acceleration. Just so you got the shapes here, guys. Okay, those are your shapes between A and E if you're looking at part B. Okay, for the total distance traveled, obviously you gotta go all the way across. So part A of the question wants us to find the acceleration between A and B. Well, acceleration is VF minus VI over T, so that's going to be 20 minus 0 over 2, okay, which is why we get positive 10 meters per second squared for part A. Okay, for part B, we want to find the total displacement to E, so that means to 8 seconds. All right, so for this first one here, we got 20 as a height times a base of 2, that's 40, divided by 2, that one's 20, okay? Now, you may have drawn these boxes a little bit differently, but in the end, it's going to end up being the same. Okay, we have a height of 20 and a base of 1, 2, 3, 4, 5, 6. Okay, so that's going to be 120 meters there. This little triangle here has a height of 20 and a base of 1. Okay, divided by 2, that one's 10 meters. And then this box here has a height of 20 and a base of 3. Okay, so that's going to be 60. And then that's it for that one. So 180, 190, 210 meters positively. Okay, because it's forward for the total displacement to that position. Okay, and then the acceleration between F and G, that's an easy one. How much acceleration is going on between F and G? None. Yeah, it's a flat line. All right, if I gave you that on a test, how many marks would it be out of? Always a big hint. Look at how many marks it's out of. If it's out of 1, there's no work involved. The answer's right in front of you. Okay? And then the total distance traveled, okay, well that means we got to add on these other shapes here. So this box here is 1, 2, 3, 4 on the base and 20 high, so that's another 80 meters. This one's 20 high by 2, okay, so that's going to be 20. And then this one here is 10 high by 1, so that's going to be 5. Okay, and when we add them all together, we should get 315 meters in total. Okay, everybody all right with that? All right, tomorrow we'll probably still work on a bit of graphing, position and velocity versus time stuff. And then on a Monday, we'll probably move on to acceleration. We'll be doing a lab with velocity versus time graphs on Tuesday. Okay, so it's kind of where we're headed here over the next little bit. All right, questions from you guys? Okay, good work today, guys.